Okay, again, for the sake of the camera, we've got a function f of xy here that we easily verify to be conservative. The x derivative of this, the y derivative of this equals the x derivative of this, so this function is the gradient of a potential function, which we could easily calculate, but I actually want to do the integrals here just to verify that all this works. Okay, we have two paths, a path C1 here and a path C2 here. Now this is pretty much equivalent to one of the WebAssign questions, but I've changed a couple of things. Since this function is conservative, the integral around C1 is going to be 0 because C1 is a closed curve. Now I haven't written the definition of C1. And C2 is not a closed curve, so we could do an integral along this path. We'd have two path integrals. So again, so C1 is closed, f is conservative, so the integral of f is 0. We want to confirm. Okay? Let C1 be defined by the vector function r equals, let's say, what the radius do we want to use for this thing? Let's take a radius of, oh, what the heck, something that the book wouldn't use, 7. At least I don't think it would, or the WebAssign wouldn't use. Okay, so let r equal 7 cosine of ti plus 7 sine of tj. So we can easily verify that the x component or the I component squared plus the j component squared is 49. So x squared plus y squared is 49. And that's the equation of a circle of radius 7 and oriented in the counterclockwise direction. So I'm not going to go over the details of that. That should be pretty clear and pretty well understood. Okay, now that's your r vector. Our parameter is t, and of course we want to specify t from 0 to 2 pi, which is kind of implicit, but we really ought to write it out. Okay, so our parameter interval is 0 to 2 pi. So partition (0 to 2 pi), and I'm not going to write out the partition. It's 0 equals t sub 0 less than t1 less than t2 dot 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 less than ti minus 1 sorry, less than ti minus 1 less than ti dot 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 less than tn equals 2 pi, and that should be something we've done a number of times, so I'm not going to take the time to write it out, and I'm not going to use up the board space. Okay, but we want to look at the typical interval t I minus 1 less than ti star, which is our sample point, less than t sub I. So that's some interval out here corresponding to r of ti minus 1, which would be this point, r of ti, which would be this point, and r of ti star, which is this point. We want to integrate, okay, well, we have them I'll write it as delta r sub I equals, obviously, r of ti minus r of ti minus 1. And this is approximately a straight line segment of length, well, magnitude of this, okay, this is going to be approximately r prime of ti star multiplied by delta ti being ti minus 1. Okay, and this is because if you just want to use an intuitive analogy, and it's not a bad way to understand it, although you need to be able to justify it rigorously if you really want a deep understanding, this is basically your speed times your time interval, which gives you your displacement. It's actually your velocity times your time interval, which gives you your displacement. This is a vector, and that vector is equivalent to, or is approximately equal to this vector. So this would be this vector is this product. Okay. Now we're not even really that interested in the vector, but we're going to be very soon, so I wanted to write it out in vector form. So the magnitude of delta r sub I is the magnitude of r prime of t sub I star times delta t sub I, approximately equal to. Now, on this interval, actually, I said we're not interested because I'm thinking of density, but yeah, we are interested in this vector function, okay? So, this is a vector function, so let's put an arrow over it, so that what we're wanting to integrate is f of xy dot delta r sub I, or what we're wanting to sum up is this f of xy dot r sub I, okay? And another way of looking at r sub I is it's a tangent vector, okay? This vector is approximately tangent to the curve, and we're looking at the tangent, the tangential component of this function as we integrate around the curve. So this is equal then to 3xy squared plus 2x I plus 3x squared y plus 5yj dotted with r prime of t sub I star. Now, of course, x and y are functions of t, and they're going to be evaluated at ti star. So we're going to rewrite this, and of course our r prime, well, you know, we can do the derivative of r very easily. I'm going to have to aim the camera just a little lower, which means we're going to lose a little bit of this up here, but we've got all the information now in front of us. We have r prime equals -7 sine of ti plus 7 cosine of tj. And now we can write all this out. And it's going to be a bit of a mess, and I don't know that I can write it out in the space I've got here. But that never stops me. I'm going to try. Okay? So this is going to be quantity 3. X is the cosine of t. And that's, of course, going to be cosine of ti star sine squared of ti. And no way I'm going to get this all written here. Now, we'll do what we can here. Plus 2 cosine of ti star, in parenthesis, yeah, don't know what to say about what I just did there, but I did it. Okay? And then it's going to be, that's times I, oh boy, I better put the I out in front here. Okay, then I'm going to move over a little bit because I know it's going to get long. J times 3 cosine squared of ti star sine of ti star plus 5 times the sine of ti star. And if I've done that accurately, then I've got this function now expressed in terms of the parameters of this tiny interval here. And of course we're going to sum that up, and that's going to give us the integral. We want to understand what's happening on the tiny interval because that's the key to setting up pretty much any integral. It's much better than following some formula we don't understand, although, you know, we can follow that formula. We want to think back to what's going on here so we totally understand the formula. We can work on understanding this from both sides. Okay, we can work on understanding it by using the formula and getting the right answer, and then thinking about what goes on here, or we could think about what goes on here and then see how that embodies the formula. Ideally, we get both understandings, which gives us the depth of knowledge and the flexibility we need to creatively apply these rules. Okay, anyhow, we have all this, and then that, I'm going to need a little parenthesis here and here, is dotted with r prime of t sub I star, which is the quantity -7 sine of ti star times I plus 7 cosine of ti star times j. Well, we just do the dot product. So this ends up being equal to, okay, it's going to be all this times the sine, which means that's going to give us a -7 times 3. So I'm going to just do -21 times the quantity, and then it's going to be a cosine times sine cubed, and then cosine times sine on the I component. And then for the j component, we're going to have a cosine cubed sine because we're multiplying by the 7 cosine. And then 5, well, we're going to end up here with 35 times the sine and all that stuff. And actually, I don't necessarily want that -21. I don't need a parenthesis there, so I'm going to write it this way. Okay, so writing it out. it's very clear how we do this dot product. All I have to do is write it out correctly. So think about what I should be doing and scream or something if I do something wrong. So it's going to be, from here we're going to have a negative 21 cosine of ti star sine cubed, right? Yep, of ti star. Okay, well that's a good start. Plus, okay, now it's negative 7 times 2. Well, let's just do a minus. Minus 14 times the cosine of ti star sine of ti star. Okay, so that takes care of the I component dotted, well, the I component times the I component here, that part of the dot product. And then we have a cosine that goes into each of the terms on the j. So that's going to be, it's a 7 cosine, so it's going to be plus 21 cosine cubed of ti star sine of ti star and then plus 7 times 5 is 35, and it's going to be sine cosine. And the one thing I neglected to write out here was a delta ti star, which is a factor of the whole thing. So it's this times delta ti star. Well, now our partition goes from 0 to 2 pi. So this is going to approach, again, when a miracle occurs that we should understand, but I don't want to belabor, because that's something you hopefully learned in first year calculus, how this approaches the limit. This is going to give us negative 21, I'm going to write it sine cubed of t cosine of t, and then it's negative 14, I'll write it cosine of t sine of t, it's arbitrary which order we use, and then it's going to be plus 21 cosine cubed of t sine of t, and so far, yeah, everything's working out. It's going to give us 0, plus 35 cosine of t sine of t dt. Okay, well, we do all this and we notice that we have an odd power of the sine here. We're going to do a u substitution equal to the cosine. So we're going to end up with a fourth power, integrating a third power of the sine. But if the sine is your u function, that's going to give us then, on integration, a fourth power of the u function, meaning the antiderivative is going to be a fourth power of the sine. Well, a fourth power of the sine is going to be equal at 0 and 2 pi. Okay, so it's going to all be equal between 0 and 2 pi, and it's going to give us 0 for the integral. Well, the same sort of thing is going to be true for every term. So every term includes an even power. Every term integrates to an even power of either a sine or a cosine. So I'm just going to say this whole thing equals 0 without going through all the substitutions. And you should do this yourself, since every term to an even power integrates to an even power of the sine or the cosine. So that's something that you simply need to understand. That's a very familiar pattern. If you were assigned enough problems, did enough problems in first year calculus, it's a pattern that should be familiar to you when you enter this course, but certainly by the time you leave this course, that pattern should be well established. So I'm not going to do the rest of the integration, and I don't want to take the time because we do need to get to Green's theorem to do the integration over this path, but I'll set up the path, except I don't know what the points were, and I didn't see any reason. The points seem pretty arbitrary here, and I'm simply not sure what the point of this broken path was. But let's just say now, if this is 7, so let's just say this is a point here, 4, 3, and this is the point, let's say 9, 5, okay? Then we can parameterize each of these paths. So we could say, for example, that to get to 4, 3, path C2, your R vector is just going to be 4ti plus 3tj, 0 less or equal to t less than or equal to 1. And then a vector from here to here is going to be 5i plus 2j. So R is going to be 5t plus 4i plus 2t plus 3j. So that here R prime is going to be 4i plus 3j, which is just a vector in the direction of this path. And here R prime is going to be 5i plus 2j, which is just a vector in the direction of this part of the path. Then we simply use this parameterization to do everything that we did here. It's going to be a lot simpler because we don't have to write out all the cosine and sine, all the cosines and sines. We just have simple coefficients. It'll be simple numbers, and we'll get it. Now, in any case, our function is conservative. Well, good time to pull out this guy. Okay, so we didn't need to do any of this. Look, our function is conservative, so to verify the nature of a conservative function here, the integrals that we get should be consistent with the fundamental theorem of vector functions. That You know, I really, to distinguish and to go on here, I should have probably used a capital F up here. So since I haven't used the F notation, except right there and right here, I'm going to go ahead and change the lowercase f to capital F so I can use the lowercase f for our potential function. Okay, so now I can say that, yeah, I probably want to talk about capital F here. I'm assuming, of course, that we're familiar with how to obtain the function. So I'm going to say that f equals the gradient of little f for little f equal to three halves x squared y squared plus x squared plus 5 halves y squared. Now if you run through a few examples of how we integrate these things, and we've been over that, you can pretty much do that in your head, but of course you know, you haven't done as many of these as I have, so you're going to be less adept at screwing it up by doing it in your head. Okay? But let's see if I screwed it up. If I take the x derivative of this, I get 3xy squared plus 2x. Well, there it is. And it's pretty obvious why that is, if you've thought through these integrals in this process. Okay, if I take the y derivative, let's see if my luck holds out, I'm going to get a 2y here, multiplied by 3 halves, going to give us a 3x squared y, which is exactly what we have here. And derivative of 5 halves y squared is clearly 5y. So the gradient will equal this. Okay, so the integral over any curve of f of r dot dr has to be equal to little f of b minus little f of a. A and B are the endpoints of C. So if A equals B, curve is closed, and the integral of f dot dr has to be 0, and that's confirmed by what we get here. Okay, if A equals the origin and B equals the 0.95, then the integral over the curve has to be little f of 9,5 minus little f of 0, 0. And little f of 9,5, now I got to do some arithmetic, it's going to be fun. Let's see, we're going to have to calculate x squared y squared. Well, x times y is 45, and the square of 45 is 2,000, 4,000, 40 plus 5, 700, no, 2,000, 4,000, got to be more than 4,900, okay, 40 plus 5, 40 times 5 is 200, it gives us 400, we add that to 4,500, we get 49, not 49. It's 2,000, okay, and 25. Okay, so it's 2,025 here, and it's 3/2 of 2,025. Okay, and then plus x squared, which is going to be 81. And the numbers aren't really important, except that you want to do the integral here and verify that these numbers work. Also verify my arithmetic, doing this in my head. Y squared times 5 is going to be 125, so that's going to be 125 halves. Okay. And you can work out the numbers there. You get something 3,037 and a half, 61 and a half, 37 and a half, 61 and a half is 98. And 81, and short-term memory is wanting to rebel a little bit, so I don't want to think that clearly. So anyhow, you add this up, you're going to get something in the neighborhood of 3,160, 3,170, and it should match what you get when you do this integral.